During the Middle Ages in Italy, a popular entertainment was from troops of traveling actors presenting what they called commedia dell'arte, the comedy of the artists. They were satirical sketches based on broad character types, and they are the predecessors of modern situation comedies. The heroes of these plays were the naive, good-hearted lovers, the country bumpkins, and the wily, street-smart trickster servants. The villains of these plays were the greedy Venetian merchants, the bravado-speaking Spanish captain, and the bombastic Il Dottore. They were all regional stereotypes, and they were making fun of the Venetian merchants or the Spanish soldiers or the university professors. Il Dottore was from Bologna, and he received his doctorate there, which the University of Bologna, famously founded in the 11th century, awarded only doctorates to its graduates. And in those plays, Il Dottore would sound out long, bombastic, gobbledygooky explanations of minutiae. And it was a grand form of comedy, and again, a predecessor of our modern American suspicions and skepticism about intellectuals who have spent too much time in their ivory towers and lost touch with reality. So today, we call such people full of baloney. And that's where that expression comes from. And I think what's a big part for me of the excitement of what we're exploring here with our review and with the Electric Universe is coming out of that realm of baloney back down to more grounded, natural philosophy, observation-based, experience-based, natural science that has a higher regard for a little bit more common sense. So we've heard about mythology. It seems absurd, as David suggested. We've seen the efforts, the Il Dottores of the modern era, right, presenting their bombastic arguments to uphold a theory that doesn't seem to be tethered to reality. So we're going to continue exploring how we tether some of these wild ideas to something tangible and concrete. And the best way to get into that is with the man who has spent his time in engineering, electrical engineering, and the study of astrophysics. So we're going to conclude tonight with Don Scott. Bring him on to stage.
Me, I hope he wasn't anyway. Good evening. As my wife Anna has told you, I've been coming to these meetings for many years now. And several years ago, we had at one of our meetings a professional astronomer who stood up on his hind legs and said, yes, we know there's electricity in the sky, but it doesn't do anything. Well, I'm here tonight to tell you that it does. And I would like to explain a few ways that I think, at least, that it does do stuff. Do things that are very, very important and have been historically important to Earth and to just about every other object in the cosmos. So if we can begin, this was really the first proof, really, I hate to use that word, but substantive indication that electricity does indeed flow in the sky. Christian Birkeland was a Norwegian scientist, explorer. He went out under the northern lights on the northern slopes of Norway and tried to take data that would show that his theory was that those northern lights, the aurora borealis and of course the aurora australis as well, are electrical in nature. And he maintained that there were electrical currents, the charge particles coming through the sky and going down into, this picture shows Earth right there. That's the little blue dot of Carl Sagan fame. And you can see there that in the magnetosphere, there are these, what I call lily-shaped cusps. And Birkeland claimed that the charges would come across from the sun and then pair down into the two cusps at the two poles. And, well, he was dogged for years by astronomers who said that was insane. One of them famously was asked one time, did Birkeland's ideas or his theories have any effect on your work? And Sidney Chapman said, no, of course not. They were all wrong. Well, it turns out that after we were able to send rocket probes up into the ionosphere just after World War II, we found those currents, and they're there. Nowadays, astronomers will be willing to call the currents that do come down into those cusps Birkeland currents, as they should be. When I talk about it, I talk about that as a Birkeland current as well. They don't like to do that. They talk about flux ropes and other sort of airy-fairy descriptions. They are beginning to try to not talk about the word Birkeland. The Birkeland currents, and you can see there at the bottom of that lotus funnel that they are squeezed together. They do come in sheaths, that is to say concentric sheaths of current, and current goes both ways on those sheaths. At the very bottom, of course, is the aurora, and the classic astronomy people, I put the word Birkeland current on there, but you notice on the diagram itself that I got from one of the astronomy sites, doesn't have the word Birkeland at all. If you look carefully, it talks about Peterson currents down there. Just earlier this year, in 2014, there was an announcement that galaxies actually are formed on strings, delicate strings. Well, I maintain that those strings are electrical currents. And these electrical currents have been found by radio telescopes, and consulting my notes, at 326 megahertz between the Coma cluster and the Abel 1367 cluster. These long strings of Birkeland currents do indeed exist, and they have been calculated because of the strength of the surrounding magnetic fields, that those currents have a magnitude of somewhere in the order, get ready for this, of 10 to the 19th power amperes. We're talking big currents, and they do indeed exist, and they do connect stars within galaxies, and they do connect galaxies in intergalactic space. The currents that we see and can take pictures of, sometimes they're quite jagged, sometimes they're quite beautiful. That looks like a ballerina to me, but that's maybe because I've been too many glasses of wine, I don't know. But other times they're quite straight, quite regular. There's an example of a very regular current. I won't call it a Birkeland current because and many people disagree with me, one of my best friends disagrees with me. I think that a Birkeland current is different from a force-free current. A force-free current in space is a current that is going along undisturbed, but any current anywhere will create a magnetic field. And so that current in space will create a magnetic field through which it itself has to pass. And if it does that, there's guaranteed there's going to be a force called a Lorentz force, which depends on the cross product between the current density and the direction of the magnetic field. And if there is a force, it's like, kids in a school bus. You're trying to get them down to the party or the lake or the convention or wherever you're taking them, and they're fighting and boisterous. And eventually, if the bus driver is good enough, you'll get them to shut up and sit down in the back and keep quiet. That's the way I think of one of these Birkeland currents. And a force-free Birkeland current is one in which the internal stresses and strains and forces and pushes and pulls have been yielded to. In nature, you know, we always hear this thing about water flows downhill, water will seek it, things will go to a lower level if you let them. Well, that's what's happening, in my opinion, in these cosmic currents that are left alone. They reduce themselves to a force-free, minimum energy, not zero energy, because obviously there is current in that. This is far from a force-free current, by the way, because it's a very powerful Birkeland current, really. But eventually it will settle down to that force-free state. I should say that the force-free current consists of the current density and the magnetic field. And the magnetic field and the current are in the same direction. So if I speak of the current, I'm talking about the magnetic field and vice versa. What's happening here in that you can see that twisted helix, there is a magnetic field component that's axial, that goes in the same direction as the current, and one that wraps around. And after doing some studying on that, I came up with a model. Unfortunately, the model that I came up with and was very proud of, I just found out a couple of days ago, was already derived by another gentleman whose name was Stig Lundqvist. Stig Lundqvist, I think, was a friend of Hannes Alfvéns in Sweden, and he derived this model for the force-free current. He called it a Birkeland current. What you're seeing here, it's very complicated looking, but the red line, the big one, is the power, the force, the strength of the magnetic field that is in line with the direction of the current. The second curve, and I don't know if you can see it, it sort of peaks out here. It's a greenish one. Forget the third curve, it doesn't mean anything. But that second curve is the strength of the wraparound magnetic field. So out of all that complex up and down, what do I want you to remember? What I'd like you to remember is that where the red curve, that is the strength of the magnetic field along in the direction of the current, it goes through a zero. See it right there? If I can hold my old shaky hand steady. There's a zero there of that magnetic field in the direction of the current. At that point, the wraparound field is at one of its, or pretty close to its maximum. The first one isn't quite exactly on, but the rest of them are. When the red curve goes through zero, the green curve is at either a positive or negative maximum. So what does that mean? Well, I got a couple of pictures here that try to show you what it means. The blue teal-colored arrows are the magnetic field as a function of if we back off away from the axis of the current. So the first picture there is what the magnetic field looks like right down on the axis, right on it's almost in the center of the Birkeland current. It's straight. There is no wraparound field. Remember in the picture, the red thing is way up, the red curve is way at the top, but the wraparound field hasn't gotten started yet. Well, if you pull it back a little bit away, pull back a little farther, like to step number 2 there, you can see that the wraparound component has begun to be seen. The straight component is getting weaker, and eventually you get to a point, well, somewhere between shot 3 and shot 4, where the only magnetic field you have is a wraparound. In fact, what happens, and I won't bore you with any further detail of that, well, unless that's sort of, I don't know if that gives you a feeling of the wrapping that happens. As you're close to the axis, the magnetic field is in the direction of the current, and then it begins to twist, and it begins to come back this way, and eventually will go back that way, and in fact, it will wrap in all directions around the current, the main current stream, much like a Roman fasce. The old Roman the fascist symbol. You take a bunch of reeds that are by themselves very breakable and very tender, very bendable. And if you push them all together and then wrap them with leather in a spiral, and then when you get up, wrap them back the other way in leather, and then wrap them this way in leather, and then wrap them back the other way in leather. Eventually, if you do this enough times, you get something that's as strong as a steel beam. That, I maintain, it makes sense to me at least, is one of the reasons why we do indeed see these cosmic currents, they're called stellar jets, that are in almost an absolute straight line and last collimated. They don't spray out like a garden hose, but they last for, well, there's the one out of M86 is 5,000 light years long. And it's just a plain stream of electrical current in space. So that is the picture of, at these very, what should I say, discrete radii, and those numbers there are just arbitrary, but it gives you a feeling for the fact that the first one out, the one that happens at 33, the radius of it is 33, is a clockwise spin. Then you go out to the next one, it's counterclockwise. And you go out to the next one, it's clockwise, and then counterclockwise, and then clockwise. So that wrapping, I won't bore you with the detail of it, but is what I think is one of the most important properties of the force-free current. There is no, in this force-free currents, there is no matter concentration. You don't get what you see in the Birkeland current there, those double sheaths as they came down into the North Pole of the Earth. That doesn't happen here. And even my critical good friend, well, I think will say the same thing. There is no matter separation, no matter concentration in a force-free current. But what can give you matter concentration is the so-called famous magnetic pinch, or Z pinch. There's also a different type of, than the Z pinch, there's a theta pinch as well. And what happens, you can see there the blue is the go-around type of magnetic field, the red is supposedly the current. If the magnetic field gets stronger, it's like tightening your belt. It squeezes it and squeezes it and squeezes it. And eventually, if it squeezes it so far, there's liable to be a reaction. And that is a very famous picture, and if you've been here before at all, I'm sure you've probably seen me or somebody, Wall or someone, put that on there. The image on the left is a real astronomical image. It's the Ant Nebula. It's well known. The middle one, I think you'll recognize, is essentially an indication that what I'm telling you is not fairy tales, that this pinch effect really does happen. And what was done in the laboratory is to put a tremendously high current pulse down through that conducting aluminum can, and the current going down made a wraparound magnetic field which squeezed the can. And that's exactly, you can do it with a stream of water from a kitchen faucet as well. If you pass a current down through the water, you can actually squeeze the stream. Let me tell you what I see in here, and maybe it's like looking at that and seeing that ballerina earlier. I hope it isn't. I think it's real. What I see when I look at this picture of the Ant Nebula is I see one of these currents, and I see that here at the upper end of it, the current, the plasma is not too visible. It's sort of getting into the darkish mode where you don't see things. And as you come closer to the center of it, as you come closer to the site of the Z pinch, the plasma gets brighter and of course changes shape. And I think that that's exactly what the mechanism that causes the Ant Nebula is the one that crushed the Pepsi can. So it's a Z pinch on a cosmic current that does that. There's another diagram that sort of shows it. the idea here is that if the Z pinch is a relatively mild pinch, it can produce those magnetic field lines that actually hold and give stability to the current. Stronger Z pinches can initiate a discharge or a short circuit. Here's, sorry, I'm a professor. I got to put a graph of something on like this on the board every time I talk. What this is in a plasma. Pick a point. Go to that. I don't know whether that exit sign is a plasma or not. But go to the typical, sign that says "Eat at Joe's." Go into that neon sign. Go into the center of that tube, and you're in the middle of a plasma. At every point in the middle of a plasma, there are really two important qualities. One is, what's the electric field there? By that I mean, what is the force per unit charge? You've got a positive ion sitting there in the middle of this thing. What is the force on him? Is it a strong force, a high E field, or is it a low force, low E field? That's, pick a point on anywhere in the diagram, at the end of the letter N there, that says that the force on a point in the plasma at that point is sort of medium. It's not way up here and it's not way down there. The other important quality or quantity associated with any point in the plasma is the current density. That says, in your neighborhood, how many amperes are going past you? How many amperes are going through every square meter, let's say, every cross-sectional unit area? If you have a lot of amperes going through a plasma, and the plasma is very big, very wide, then it doesn't mean that the current density is very large, because if the cross-sectional area is big, well, you can get a lot of amperes through there without squeezing. If the cross-sectional area of the current is smaller, then of course the current density is higher. And so you would take that point at the end of the N and stick it over here or over here. And there are really three main modes of operation of a plasma. This is to be an exam at the end of the week, okay? The dark mode, you can't see it. The ionosphere of the Earth is in dark mode. You know it's there because you can bounce radio signals off it, but it's not visible. Except in the aurora, when it jumps from being in the dark mode to being in the glow mode, and it glows, and you can actually see it. So the difference between a plasma in the dark mode and a plasma in the glow mode is one simply of current density. So if there's a lot of amps running through this thing, and at the bottom of that funnel, you've really compressed that current cross-section of that cosmic current. And so the density, current density, goes up. And I maintain that at the center of one of these, like the Ant Nebula, you've also gone and popped it into the arc mode. And that's that bright star-like object. Maybe it is a star. Maybe it is the beginning in the cosmos of a new star. I would like to say one thing. I don't know if there are any of the Sapphire people here or whatever, but I've heard people say, we've looked at this plasma and we don't see any arc in there at all. There's no arc discharges in there. A lot of people confuse the word arc. Arc has two meanings. One is a jagged lightning bolt, a lightning bolt discharge. It's an arc discharge. That's true. But not all arcs are lightning bolts. If you look into the arc light of a motion picture projector in a typical motion picture camera, a motion picture projector theater, you've got two electrodes that come together and an arc is struck. You pull those electrodes apart and what you get is not anything that looks like a lightning bolt, but it looks like a sheet of flame. So arc discharges are arc discharges not because of their shape, the lightning bolt shape. They're arc discharges because of what they emit. And the one big difference between the arc discharge and the glow mode discharge is that the arc discharge, well, you know, if anybody done any electric arc welding, copious amounts of ultraviolet. If you look at an arc welder, that's an arc welder is at perfect example. If you look at an electric arc welder, between the tool and the workpiece is not a lightning bolt. It's like a sheet of flame. The best arc welders look like gas welders. I mean, they look like flame. And so you can't look at a plasma with the naked eye, nor should you, if you think it's in a glow mode, ever look at it with your naked eye. You should use ultraviolet protection. And if you want to know, is my plasma in ultraviolet or is in arc or glow mode, see if it's putting ultraviolet out. Anyway, end of that mini lecture. There's all sorts of things I can tell you about that diagram. Well, one of the interesting one is number 4 down here, is there are certain parts of this diagram that have what's called a negative slope. There's a negative slope. These are positive slopes. They're rising with increasing current density. But right in here is a negative slope, and certainly in the arc mode, in the beginning of the arc mode, there's a negative slope. And that means if you're a particle in a plasma and you're sitting up here, like right there near where that arrow is, what are you sensing? What's at your point? The answer is it's a reasonably high electric field. You're pretty high up on the axis here, but you are not at well. For the glow mode, you're not in particularly heavy current density. And you say to yourself, gee, I don't like to be pushed around. I don't like to have a force on me. Water flows downhill, right? So the plasma will say, I can reduce the pushing and pulling that I'm suffering by going down the chute down to here. Well, how do I do that? Well, I move from left to right and go down. I reduce the electric field on me, and I increase the current density. How are you going to do that? How's the plasma going to reduce its current density? Increase its current density. It goes higher, right? It automatically, I shouldn't say it takes itself into its own head because it doesn't have a head, but it makes filaments. It says, why should I use my whole area here to go down when I can clamp down and make a filament here and nothing in the middle. So if you see a plasma in a place like this, you will expect, if it's got a negative slope to it, that it will form filaments. And so I submit to you that the reason that lightning bolts are jagged, what you call lightning bolts, is because they form filaments, and there's a natural tendency to filament here. There's also a natural tendency to filament here at the breakdown between dark mode, where you don't see it, and glow mode. You know what was a perfect example of that? It's the outer regions of our sun's corona. If you ever looked at a picture of the sun in a solar eclipse, you see the corona is very bright around the sun. And the farther out you get in the corona, you see these striations, these fingers reach out. And that's what's happening there. So, okay, that's a mini lecture on plasma. Why did I put you through that? Well, because I'd like to talk a little bit about what I think at least happens in one of these pinches. If you up the current, that's the red arrows, you up the B field going around, and you'll get a pinch. So I'm suggesting as a sort of an ideal model that instead of crumpling it up like the Pepsi can crumpled up, let's say it just sort of crunches down, and what you get from this point down to this point is a cone, okay? Can you see it getting smaller? And then beyond the pinch point out here, you're getting a widening out cone, okay? So what's happening as the charges come in, as this current comes in here, it may well be in the dark mode. If it's a minimum energy current, a force-free current, a field-aligned current, it may be very quiescent and be in dark mode. You might not see anything. Remember in the Ant Nebula, out at the ends? You don't see anything. So it may well be that that's dark mode plasma. And as you get in what happens at the beginning of the cone as the thing narrows down, as you squeeze that cross-section? You got the same amount of current. I mean, you can't have more current over here than you have over here. In a wire, the current's the same no matter where in the wire you measure it. So if you squeeze the wire down, you get the same amount of current going through the squeeze point, but you have a higher current density. And on that previous slide, what happens when you increase the current density? You pop the plasma from dark mode into glow mode and maybe into arc mode. As you get farther and farther down that cone until finally right in the middle, I'm suggesting you get, if the thing works like a picture I'm going to show you in a minute, that is an arc mode discharge. And what happens is there's an arc mode discharge, or possibly glow mode discharge, from both sides of this thing, this crimp point. And they look like, I've tried to draw them in here in light blue. They look like a pair of umbrella shapes, smushed together. Sort of like you take two torpedo shapes and push them together so they smash in each other's nose. You see it? There's one torpedo that goes around this way, and the other torpedo or umbrella, if you're more pacifistic than I am, an umbrella-shaped thing, goes around that way. And the intersection of the discharges with the shells of conductive material they are always at right angles. Electric fields always impinge on a conductor orthogonally, straight in. They don't come in this way. They come in straight down. And so if you notice, I've tried to draw the blue curve orthogonal to the slope of the cone. You see that? So what will happen here is that the discharge, this curved discharge, will move out toward the left. Why? Because between this point and this point, the voltage is the same as it is between this point, and therefore the electric field between here and around this way is higher, is stronger electric field than it would be if you move the discharge out to, let's say, around there. The discharge would still come in perpendicularly to the surface, okay? And you can say, well, gee, why are you beating your gums about this? Why is this so important? Well, it's so important because this is what happens in a Z-pinch. This is the important mechanism by which we believe, I believe certainly, that stars are formed. And it's that crunch in the middle that, it's not an accretion disk. That across there, it may be a disk, that surface looks like a circle, but it isn't an accretion disk. It's a Z-pinch disk, and that's where the compression comes from. So if you ask the typical astronomer, you know, what goes on in one of these pinches, they know they exist. You will get that as an answer. I hope you folks in the back can see it. But do you see the labels on there? It says black hole, accretion disk, and magnetic field lines. There's no such thing as a magnetic field line. Just like there's no such thing as a line of constant altitude in a topographical map. It's a very convenient thing, and it brings a lot of information to the people who use it. Very useful, but it's not a real thing. You shouldn't reify it into being something real. And astronomers have done that with magnetic field lines. And when they talk about reconnection of these field lines, it's like they really exist. You grab this one over here and stick it over here and put them together. There's no such thing. It's like worrying about whether Pinocchio is going to have a fight with his brother. They don't exist. So anyway, there's a real one. That, I think, is one of Dave Talbot's favorite words is archetype. And that is my archetype. That is an archetype Z-pinch. And I'll point out some of the things that are obvious, and if you listen to me carefully, and I haven't put you to sleep yet, you'll realize what I'm saying here. Look down to way down to the lower left and way out to the upper right, disappears. That's right, because the plasma there is in dark mode. But as you approach the pinch, as you start squeezing down on this, you pop that plasma, both ends of it, into the glow mode. So the greenish things here and here, you can see you get less of the black stria through it. The whole plasma goes into glow mode. Here there's like partially, some of it's glow and some of it's dark mode. But eventually up in here, it all becomes glow mode. Also, you see two sheaths. There's one sheath here and an inner sheath. Remember that picture of the Birkeland current? There's one sheath within another. That's the same thing that happens here. And it happens on both sides. You can also see, I hope, my two umbrella-shaped, overlapping umbrella-shaped, paraboloids? We'll call them torpedoes crashing together, whatever. The middle business is sort of interesting too. This, through here, this thing, this thing, this thing, and this thing are called double layers. Double layers are a plasma phenomenon that happen under very heavy current conditions. And in the center of this is typically of this kind of configuration, the currents are the heaviest in the center, and then in the outer shells, they're less and less and less. So anyway, here's another picture of, this is, if I had more time, I would talk to you about the making of concentrated shells of material. What I claim, and my friend I'm sure will disagree with me, but what I claim is that if you squeeze this thing, this force-free, field-aligned current, squeeze it down, what are you doing to it? You're increasing the current density. And if you increase the current density, it's the same thing, really, as not squeezing it, but increasing the current. And if you do that, you can show by Lorentz force rules that matter will be moved from regions like this into regions like that. The black arrows along the 3 o'clock horizontal plane show the directions in which matter will be moved. This matter concentration will not occur in a force-free current. But I suspect, and I think it will, if you squeeze that force-free current into a Birkeland current, and we've seen pictures of the Birkeland currents, so we know what they look like. You saw that picture of that last picture of the object was a Minkowski 2-9, I think. And that's a planetary nebula. The Minkowski is not the Minkowski of Minkowski space. It's another much younger guy who is an astronomer. In any event, that's what you'll get from the typical astronomer, okay? They absolutely refuse to use any electrical kind of voltage, electric field, current density. No. They talk about bow shocks, ladder rungs, wine glass parabolas, hyperbolic arcs. Now, how the parabolic arc changes into a hyperbolic arc, I don't know, but I don't know. I don't think anybody's measured that closely. And of course, in the middle of the whole thing, instead of my arc discharge, they've got a dust disk. They will not give up the accretion disk as a figment of their real imaginations. It's all garbage. None of it exists. It's all electrical. And what you see back here may indeed be vortices, but they're not hydrodynamic vortices. They're electrical vortices. So that's what you're going to get if you look up Z-pinches from an astronomer. Here is just, I think, one of the best examples of the fact that this thing really does work. Here is a current, and it's suffering obviously multiple Z pinches. And when they discovered one of these objects, there were two astronomers. Their names were Herbig and Harrow. So they got credit for this, and they called objects, and now there's more than one, Herbig-Harrow objects. This is Herbig-Harrow object number 111. And you can see that there are periodic Z pinches. Tony Peratt calls that the sausage instability, because they happen in a periodic way. If any electrical engineers have studied electrical transmission lines, you know that there's pulses back and forth on electrical transmission lines. If they get out of control, you have northeast blackouts every once in a while. There, I submit, is a perfect example of that. That thing is like a big transmission line. And there are all sorts of pulses, and when the pulses come up together, that's where the Z pinch happens. And it happens periodically all the way down the jet. Here's a picture of that one, and you can see it actually moves. And that set of pictures was taken between 1994 and 1998. That's how much it moved in 4 years. So when Dave Talbot first came up with this idea of a polar configuration of a bunch of planets in a line, the astronomers just about broke up laughing. That was so stupid that they could never imagine anybody would ever think about a stable configuration of objects in a line like planets on a shish kebab. Okay, there's the shish kebab. It's real. And then you can see the one in the front is sort of getting a little bit expanded as it goes along. But it does move. And there are many more of these. So this is a bunch of essentially proto-stars in a row. All this points out is that this configuration is indeed stable and can exist. You don't need to have stars in circular orbits around a center star, sun, whatever, in order to exist. This is another one, the number of that's HH34, I guess. There's another one, they go on. There's many of these. And they all were looked very askance at by astronomers when they were first discovered. If you go and ask NASA to describe this HH111, that's what you're going to get. That is a NASA artist's conception of what Herbig-Harrow 111, this one right here, they think this is what this looks like. And of course, it's got the accretion disk, and it's got a dust torus, okay? Nothing electrical. Anyway, I can go on forever now showing you these things that, 20 years ago were inconceivable. There are many of them in space now. There's just one constellation, and each one of those is labeled as a Herbig-Harrow object. If you use a big scope on it, you'll see the pinballs in a row. There's the best drawing that I've come upon that shows what happens at a Z-pinch, at a normal Z-pinch. If I were to draw this, I would draw this purple line continued down around the bottom of the blue and back up there. And that would be one of my umbrella-shaped surfaces. Do you see what I'm saying? This purple would come up over the top and then back down here. That's what I think happens. That's why that blue central, almost spherical body, how it's formed. It's the overlap between those arcs, those discharges in the Birkeland pinch, in the Z pinch. This is a picture sent back, well, it's a combination. I kind of cheated. Half of that picture was sent back by the IBEX mission. And the IBEX mission is the Interstellar Boundary Explorer. And they maintain pretty much that they have discovered certainly a spherical thing inside which our sun, the little tiny dot in the middle, is center of. And it is a trail, and they've taken pictures of the trail. Now, whether they've turned the camera around and looked for the other tail, which of course is the one down here, I don't know. So this one is I cheated a little bit. I duplicated the upper half of this picture and turned it upside down and stuck it on the bottom, because that's what I think happened. And I think that will eventually be found. But so far, IBEX has found only the top part. Now, Wal Thornhill and I are very good buddies, and so I unabashedly stole from him that picture, which he made up. And you can see there are some differences, but not a lot. If I were to draw this over again, I would make this thing come in more parabolically and out that way, and I'd make this one come up around the top and come back down parabolically that way. We don't know where these areas here are, but we know they exist. That's what IBEX has found. They found that there are heavy concentrations out in the plane of the solar system of where electrons combine here with solar ions to form, what is it, excited, am I saying this right? What is it? It's an excited nuclear atom. Neutron, I see it, I said that. But the E is what's bugging me. I think it's excited. Anyway, that's just like what happens in a plasma tube. In a plasma discharge, you've got an anode over here and a cathode over here, and you got ions going one way and electrons going the other way. Think about that for a second. You're an ion, okay, and you're in the middle of this plasma discharge. Which way are you going to go? You're going to head toward the cathode, because that's negative, and you're positive. You want to go negative and positive attract. You don't want to go to the anode. He's positive too. That repels you. So you go screaming down there. You're an ion toward the cathode. What happens when you get to the cathode? There's a sign that says no ions beyond this point, because ions can't go in wires. Ions live and die inside the plasma tube. Electrons go into wires. So if you have an electron that's going down this way, it'll go into the anode, into the wire, and all the way around through the power supply and come back out the cathode again and get into the plasma tube. But the ion, The ion has to stop. And when it stops, it recombines with an electron and becomes neutral. That's what they found. A whole bunch of excited neutral atoms. And they bunch up. And one of the investigators for the IBEX mission said, it's kind of like you pour maple syrup on your pancake. And when you do that, it all sort of, the maple syrup sort of piles up a little bit and then eventually oozes down over the sides of the stack. And what we're seeing in these areas, and of course this and this are part of a circle. That's just the thing in cross-section, right? So what we're seeing here is a pileup of the maple syrup. But it works exactly like a plasma discharge tube. And anyway, Wal's also included here. These pictures are pictures of the Z-pinch. And remember, David talked about the necklace with the points around here. This is an example of the filamentation process going on, that the plasma is forming filaments, individual filaments, not just a sheet of plasma. And so this is what we think is going on, or at least did go on, when the sun and the solar system, the original solar system, which did not include Saturn, Earth, Mars, Venus, it included maybe Uranus and Neptune and maybe Jupiter, but nobody knows really. But this is what forms a star. This is the process by which that star can form, and it ain't going to happen with accretion disks. This is what you used to hear from astronomers. They have since realized there is no such thing as a bow shock out there. What we just saw on the previous slide is pretty much, they don't admit it's electrical, of course, but they admit that the geometry is pretty much the same. The IBEX mission discovered, that's the IBEX ring. That's that ring of ENAs that are out there that are piling up. It's an excited neutral atom surround the heliosphere. And as I said, this is very similar to what you see in a discharge tube. That's
What's an excited neutral atom?
moving, hot, lots of motion to it. It's been banged around. It's not just placid. The standard description omits any discussion of a Z-pinch. That's not far off. You see what happens? See what comes down and what happens in the middle? They're getting the picture little by little. But of course, it's not electrical. This suggests that our sun's heliosphere may be formed by a similar Z-pinch. That's what I just said. And there is, I took the liberty to draw in what I think those parabolic arcs should be, those two kissing zeppelins or intersecting umbrellas. Just think of scaling this whole thing up. That's maybe the way our star, our sun, was made. Maybe the way all suns are made. But could it be that if you step it up, that's also the way those galaxies were made? And it could well be. They said those galaxies were connected by strings. Well, this is a picture of, any of you folks see this? The ghostly bubbles. The electric universe doesn't use words like mysterious, dark, ghostly. That's for NASA. These are the ghostly gamma rays. And they were discovered by the Fermi gamma ray telescope, and they exist there. And I think maybe I went through that thing too fast. I'm sort of proud of my superposition of the ghostly bubbles on top of that. It makes sense. It makes a great deal of sense. Just to finish up, there's the ghostly gamma rays on their own. We can't see our galaxy, obviously, so that's an artist. You can't get outside of it to see what it looks like, but that's probably pretty much what it looks like. Here's another thing that they are good at. What's the center of the Milky Way? Again, I'm not asking you guys to really believe this, but I'm suggesting it maybe. Could that be a Z-pinch? On the upper left, do you see the umbrella shape going out? I don't see anything on the lower right. But if you listen to NASA or any of the astronomical organizations, they will tell you that at the center of our universe is a black hole. Well, I'm sorry, gang, that does not look like a black hole to me. Besides, you can't see black holes, so how do they know? Anyway, this may be what is at the center. Is it suggestive of a pinch? I think it is. But anyway, it's not a black hole because you can't see black holes. This is a picture. I think Dave used this as an advertisement for this conference. This is a real image taken in the direction of what we think is the center of the Milky Way galaxy. And NASA says that there is a great deal of evidence that just to the right of the center of this, there's a supermassive black hole at the galactic center of the Milky Way. Otherwise, it couldn't have formed. It takes your choice, I guess. But anyway, there's more to come in the next discussion. Thanks very much. into those cusps Birkeland currents, as they should be. And when I talk about it, I talk about that as a Birkeland current as well. They don't like to do that. They talk about flux ropes and other sort of airy-fairy descriptions. They are beginning to try to not talk about the word Birkeland. The Birkeland currents, and you can see there at the bottom of that lotus funnel that they are squeezed together. They do come in sheaths, that is to say concentric sheaths of current, and current goes both ways on those sheaths. At the very bottom, of course, is the aurora, and the classic astronomy people, I put the word Birkeland current on there, but you notice on the diagram itself that I got from one of the astronomy sites, doesn't have the word Birkeland at all. If you look carefully, it talks about Peterson currents down there. Just earlier this year, in 2014, there was an announcement that galaxies actually are formed on strings, delicate strings. Well, I maintain that those strings are electrical currents. And these electrical currents have been found by radio telescopes, and consulting my notes, at 326 megahertz between the Coma cluster and the Able 1367 cluster. These long strings of Birkeland currents do indeed exist, and they have been calculated because of the strength of the surrounding magnetic fields, that those currents have a magnitude.
During the Middle Ages in Italy, a popular entertainment was from troops of traveling actors presenting what they called commedia dell'arte, the comedy of the artists. They were satirical sketches based on broad character types, and they are the predecessors of modern situation comedies. The heroes of these plays were the naive, good-hearted lovers, the country bumpkins, and the wily, street-smart trickster servants. The villains of these plays were the greedy Venetian merchants, the bravado speaking Spanish captain, and the bombastic Il Dottore. They were all regional stereotypes, and they were making fun of the Venetian merchants or the Spanish soldiers or the university professors. Il Dottore was from Bologna, and he received his doctorate there, which the University of Bologna, famously founded in the 11th century, awarded only doctorates to its graduates. And in those plays, Il Dottore would sound out long, bombastic, gobbledygooky explanations of minutiae. And it was a grand form of comedy, and again, a predecessor of our modern American suspicions and skepticism about intellectuals who have spent too much time in their ivory towers and lost touch with reality. So today, we call such people full of baloney. And that's where that expression comes from. And I think what's a big part for me of the excitement.
So if we can begin, this was really the first proof, really, I hate to use that word, but substantive indication that electricity does indeed flow in the sky. Christian Birkeland was a Norwegian scientist, explorer. He went out under the northern lights on the northern slopes of Norway and tried to take data that would show that his theory was that those northern lights, the aurora borealis, and of course the aurora australis as well, are electrical in nature. And he maintained that there were electrical currents, the charge particles coming through the sky and going down into, this picture shows the Earth right there. That's the little blue dot of Carl Sagan fame. And you can see there that in the magnetosphere, there are these, what I call lily-shaped cusps. And Birkeland claimed that the charges would come across from the sun and then pair down into the two cusps at the two poles. And well, he was dogged for years by astronomers who said that was insane. One of them famously was asked one time, did Birkeland's ideas or his theories have any effect on your work? And Sidney Chapman said, no, of course not. They were all wrong. Well, it turns out that after we were able to send rocket probes up into the ionosphere just after World War II, we found those currents, and they're there. Nowadays, astronomers will be willing to call the currents that do come down of somewhere in the order, get ready for this, of 10 to the 19th power amperes. We're talking big currents, and they do indeed exist, and they do connect stars within galaxies, and they do connect galaxies in intergalactic space. The currents that we see and can take pictures of, sometimes they're quite jagged, sometimes they're quite beautiful. That looks like a ballerina to me, but that's maybe because I've been too many glasses of wine, I don't know. But other times they're quite straight, quite regular. There's an example of I think a very regular current. I won't call it a Birkeland current because and many people disagree with me, one of my best friends disagrees with me. I think that a Birkeland current is different from a force-free current. A force-free current in space is a current that is going along undisturbed, but any current anywhere will create a magnetic field. And so that current in space will create a magnetic field through which it itself has to pass. And if it does that, there's guaranteed there's going to be a force called a Lorentz force, which depends on the cross product between the current density and the direction of the magnetic field. And if there is a force, it's like kids in a school bus. You're trying to get them down to the party or the lake or the convention or where you're taking them, and they're fighting and boisterous. And eventually, if the bus driver is good enough, he'll get them to shut up and sit down in the back and keep quiet. That's the way I think of one of these Birkeland currents. And a force-free Birkeland current is one in which the internal stresses and strains and force
of what we're exploring here with our review and with the electric universe is coming out of that realm of baloney back down to more grounded, natural philosophy, observation-based, experience-based, natural science that has a higher regard for a little bit more common sense. So we've heard about mythology. It seems absurd, as David suggested. We've seen the efforts, the il dottores of the modern era, right, presenting their bombastic arguments to uphold a theory that doesn't seem to be tethered to reality. So we're going to continue exploring how we tether some of these wild ideas to something tangible and concrete. And the best way to get into that is with the man who has spent his time in engineering, electrical engineering, and the study of astrophysics. So we're going to conclude tonight with Don Scott. Bring him on to stage.
Me, I hope he wasn't anyway. Good evening. As my wife Anna told you, I've been coming to these meetings for many years now. And several years ago, we had at one of our meetings a professional astronomer who stood up on his hind legs and said, yes, 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 we know there's electricity in the sky, but it doesn't do anything. Well, I'm here tonight to tell you that it does. And I would like to explain a few ways that I think, at least, that it does do stuff, do things that are very, very important and have been historically important to Earth and to just about every other object in the cosmos.